All right, so we're going to go ahead and continue with example 3.8 and 3.9 in our textbook. We were looking at the dragster problem here. We have an average acceleration A equal to 26.0 meters per second squared. And we suppose that this dragster accelerates from rest. So our initial position, we're going to go ahead and say that is 0 meters and that they start from rest. So our initial velocity is 0 meters per second. Okay. And they accelerate for a time of 5.56 seconds. Okay. We want to know how far the dragster travels in this time. So we want to find x. Okay, so let's go back and look at our equations and try to figure out what we can use. So again, we know our acceleration, we know our initial velocity, initial position, and our time. Okay, so with all that, and that we want to figure out our final position, it looks like this equation will be what we use. Okay, so x equals x naught plus v naught t plus 1/2 at squared. Okay, so x equals x naught, which is 0 meters, plus v naught, which is 0 meters per second, times t, plus 1/2 a, which is 26 meters per second squared, times t squared. Okay, so we can plug that into our calculator. Obviously, these first two terms are 0. So we have 1/2 times 26 times 5.56 squared. So our final position x is 402 meters. Okay, I rounded up a little bit. All right, so that's for this first part. Now this second part states calculate the final velocity of the dragster in this problem without using information about time. Okay, so now we're going to pretend that we don't know anything about time and find the final velocity. Okay, so let's go back. So we're going to ignore time, and we're trying to find the final velocity, so this one doesn't help us. So this is the only one that we're going to be able to use for this problem, this equation here. So v squared equals v naught squared plus 2a delta x. Okay, so v squared equals v naught squared plus 2a times our change in position. Okay, so v naught squared, or actually I can go ahead and solve for v. It's going to be square root v naught squared, that is just 0, okay, times 2 times our acceleration, which is 26 meters per second squared, times delta x, which is just the same as x since our x naught is 0, but you can plug it all in here. Okay, and then we'll take the square root. So we have 2 times 26 times our answer from above, and then take that square root. So our velocity, our final velocity, is about 144 or 145, rounding, meters per second. So this is our final velocity of that dragster in 5.56 seconds. Okay. All right, let's do another example here. Example 3.10. On dry concrete, a car can decelerate at a rate of 7 meters per second squared, whereas on wet concrete, it can decelerate at only 5 meters per second squared. find the distances necessary to stop a car moving at 30 meters per second on dry concrete and wet concrete. So that's going to be the first portion. Okay, so let's go ahead and focus on that first. So let's see. So when we're decelerating, we're saying that that's going to be the negative of this rate here. Okay, and then find the distances necessary. So I'm going to go part A for the dry. So that's going to be, okay, A equals -7 meters per second squared. And my velocity, my initial velocity is 30 meters per second. And we want to stop the car, so our final velocity will be 0. Okay? So we want to know our distance necessary. So let's think about what equation we should use here. We want to know a distance. Say we start at 0 or end at 0. It doesn't really matter, but we want to know that change in distance, that total distance. Okay, so we don't have a time, so these are out of the question, so we will need to use this last one that we just used. So v squared equals v naught squared plus 2a delta x. So we're going to look for that delta x. So we can say delta x equals what? V squared minus v naught squared divided by 2a. Okay? All right. So our final velocity is 0. Our initial velocity is 30. And I'm going to keep the units off for just a moment. And then 2 times our acceleration, which is going to be -7. Okay, so it'll be 30 squared over, so 30 squared over 2 times 7. And we get, there's a negative on top and bottom, so we get 64.3 meters. So this is how long it would take on dry concrete to stop from 30 meters per second to stopping point. Now for B, delta x is going to be, again, 0 minus 30 seconds, or I'm sorry, 30 meters per second, divided by 2 times our acceleration is now at 5 meters per second squared. Oh, I didn't need to put that. There we go. So now it's 30 squared over 2 times 5, which is going to now be 90 meters. Okay. So let me reiterate this. So we have a car and we're going 30 meters per second. Okay. And on dry concrete, we can decelerate our car in 64 meters. Okay. On wet concrete, so when it rains, it takes 90 meters now to stop that car. Okay, so just think about this when we are driving. I guess we can really think about this and how long it takes for your vehicle to stop when you have dry conditions versus wet conditions. This isn't a lecture to try to help you guys be safe, but it kind of proves the point right here. And that physics has real life application. All right. So now it states for part C to repeat both these calculations and find the displacement from the point where the driver sees a traffic light turn red, taking into account his reaction time of 0.5 seconds to get his foot on the brake. So now we want to find the distances necessary when he has to react to the traffic light. Okay, so we'll have to now look at this. So we want to take into account time. Okay, so I believe we will need to use this equation here. Okay, I'm sorry, I meant this equation up here. So we're looking at the reaction time. Okay, so this is just going to be purely looking at how long it takes for this person to start stopping the vehicle. Okay, so we have x that is unknown. Okay, our initial x naught is 0. Okay, then our velocity is given to us as 30 meters per second. Okay, so we've got for reaction time, x, I'm just going to say reaction down here, we have x naught, which is 0, plus velocity, which is 30, okay, and our time, which is 0.5 seconds, okay, so 30 times 0.5 is 15 meters. Okay, so it takes 15 meters to react to the traffic light. Okay, so to find out how long it takes for the person to react and to stop, or the distance it takes, is going to be the change in x plus this reaction time. So if we say x tot, comma a, it'll be 64 plus 15, which is what? 64, 15, it's about 79 meters. And then for the other one, 90 and 15 is 105 meters. So assuming it takes you 0.5 seconds to get your foot on the brake, now it takes 79 or about 80 meters to stop in dry conditions and about 105 meters to stop in wet conditions. Okay, so again, just taking that stuff into consideration when driving is probably a good idea. Okay, so now we're going to look at two-body pursuit problems. Okay, so this is going to be the motions of objects that are coupled together. Okay, we're going to look at example 3.13. A cheetah waits in hiding behind a bush. The cheetah spots a gazelle running past at 10 meters per second. At the instant the gazelle passes the cheetah accelerates from rest at 4 meters per second to catch the gazelle. How long does it take for the cheetah to catch the gazelle? And what is the displacement of the gazelle and the cheetah? Okay, so we're going to learn through an example here. And instead of starting it in this video, I'll go ahead and start on the next video.